last class we saw uh, the application for variable reluctance type pressure sensor. Variable reluctance type pressure sensor, which, as I said, has a specific application, and this type of sensor is quite difficult to make, and hence they are very expensive. Okay. Tens of thousands of rupees, and if you really want certain tight specifications, it may go even to 1 lakh rupees per variable reluctance type pressure sensor. Right? You can Google search and find it yourself. Apart from these two, there are some miscellaneous inductive pressure sensor. One is called proximity sensor. So we simply have a coil, right? And if there is an object, of course the object has to be metallic. If it is ferromagnetics, much better. Right? This is very good, but this also will work, right? So if I look at the inductance, if the object is present, then I will get L1. If object is not there, right? If object is not present, I will get L2. So if I look at between presence and not presence of the object, right? Object, and I look at the inductance, there will be, this will be L1 and L2, or vice versa. Sometimes when the object is present, inductance actually reduces, especially for highly conductive objects, but there would be a distinct difference. So one way is to sense this and say whether there is an object or present or not, right? So such a sensor is called the proximity sensor, and the inductive type proximity sensors are quite popular, right? And sometimes they are also magnetized, in a sense. We put the same sensor, but we put a magnet here, right? So this becomes North Pole, this becomes South Pole, and you have, so when the object moves, right, now this has to be dynamic, you get an induced EMF, right? This will be an induced EMF. So suppose, let's say you have objects moving on a conveyor belt and you want to detect them, you can use the inductive type proximity sensor. There is another inductive type proximity sensors called electrodynamic sensor. As the name indicates, this transducer again is cannot work on static inputs, only for dynamic inputs. The principle is very simple. We have a magnet south, and then we have a coil surrounding that, right? And if you move the coil up and down, I will get an induced EMF across the coil. So this is the principle of electrodynamic coil. Uh, Even today, this is very popular, electrodynamic microphone, right? So if I look at uh, the microphone, so you have the diaphragm. The diaphragm is attached to a coil, right? So you have a coil here, and the wires are taken out, and you have a magnet that encompasses. So this is a magnet, so this is again center like this. As we speak, right, as we speak, I'm not a good. The pressure waves get generated, right? Uh, Sound pressure level, and that makes the diaphragm to vibrate and the coil to vibrate, so you get an induced EMF. Assume that this person is whistling, so there will be one frequency, right? And we also assume that this is P max sine omega t, right? That would modulate the coil, and the induced EMF would be d by dt of Pm sine omega t. That would be equal to omega Pm cos omega t, right? So that would be the induced EMF here. This is the E plus minus. So we see that the output is proportional to the frequency. So if I draw the frequency versus response characteristics, it will start from 0, because when I have DC, there's d5 by dt would be 0, and hence I will not get any output. So this is 0, this is higher frequency. So if you are using an electrodynamic transducer, you must understand that it has characteristics which is frequency dependent, right? So as frequency increases, my sensitivity increases, right? At 0, the sensitivity is 0. At some other frequency, sensitivity is 0. So whenever we use a electrodynamic type of transducer, we always use what is known as compensating characteristics. So we put, so this is signal conditioning circuit, right? And that would compensate and will give us uh, more or less a characteristics that we deserve, right? So as I said, the moving coil microphone, as it is called, is very popular. Or simply it's called dynamic microphone. Okay. The one problem with the dynamic microphone, of course, it's very sensitive to vibration. So if there are vibrations, it will easily pick up. And the second is that its low frequency response is poor, right? This kind of inverse characteristics, you can only compensate up to a certain level. Hence, uh, the output bandwidth is not very good, especially at the lower end. Uh, Lower end, the d5 by dt kicks in, whereas at the higher end, the stiffness of the diaphragm would prevent it from oscillating at that frequency. But for the microphone, we need something like 20 hertz to 20 kilohertz, which is not a big problem. We can design. You can even buy from standard manufacturers the electro dynamic type microphone. And the electrodynamic type transduction process is also used in the reverse as actuators. Right? So the one application is of course speakers. Right? So if you look at a speaker, the speaker will have right, and the coil will be inside, and this coil, because you connect output, is connected to a exponentially increasing structure that gives you a best coupling to the air, right? So if I send a signal, the coil will vibrate, and that vibration will be transferred to the speaker cone, and you hear the music, right? And in your headphones, in your computer, wherever you see speakers, right? So you will always use the dynamic transduction principle. Of course, the reverse order is not a transducer in the sense that we use transducer for, but it is an actuator. It converts electrical signal into sound signal. Okay, and the other one is electrodynamic shakers. Right? Sometimes you may have to put a instrument and then vibrate it to check whether it can handle 1G vibration or 2G vibration, 3G vibration, and so on. That means you have to shake this platform. Once again, you put a coil here and a magnet here, and supply current to the coil, the table will shake, right? You can you need not only use sine wave, you can use different waveforms and get all kinds of scenario in creating the vibration and testing an instrument. Please remember, this is test instrument, this is the vibration table, this is magnet plus coil to vibrate the table, right? This is another application for inductive type of sensors, and in the past they were also used for various other applications which no longer exist. For example, I don't know whether you have heard of gramophones. So these are discs with grooves that I'm putting a very big spiral, but it will be very, very, very small, right? And the music is recorded on this, and you put a needle, and the needle will vibrate when the disc rotates, and you attach needle to a small magnet and put a coil around it and take the output. So again, this is called dynamic pickup. If any of you have used a gramophone record, most probably you would have come across this. The Other application is the tape recorder. Right? So you have a soft ferromagnetic tape, and what you do is you create, right? So you have the, right. So you put the speech signal or music signal inside, and you move the tape. The magnetic field created by this is called tape head, tape record playback. So it records magnets north south here, north south here, north south here, and so on. So that is small magnets are recorded on the tape, and you wind the tape and again move it across the head, you get back the signal. Here again, because the uh, principle of operation is electrodynamic type, you get the frequency characteristics. Higher the frequency, better will be the response. So you need to offset it, put an inverse characteristics in the playback mode, so that you get almost a flat, right, flat characteristics for whatever frequency that uh, you want the system to work. Once again, the tapes are all thing of the past. Nobody uses a tape. Today, everything has become digital, and you record digital. Uh, the initially when the data was recorded on magnetic discs. Once again, you have a disc, so you have tracks, right? And you put a magnetic head. You have a coil here, and if it is 1, you send a positive pulse. If it is 0, you send a negative pulse, and that gets recorded on the magnetic medium. Even today, if you have a 1 terabyte or 500 GB hard disk, the recording is done like this. Only thing is, we don't use the vertical coil. We have a slightly uh, 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 differently structured coil, so that instead of having creating a north-south magnet here, this creates north-south in the vertical direction to the magnetic disk. The advantage is that you can have very high density of ones and zeros recorded on the in one track. Okay. Uh, Earlier, feedback playback was also using an inductive pickup head, but today no manufacturer will use a inductive pickup head, mainly because it's not that sensitive, especially vertically recorded magnets. So we use what is known as tunneling magnetoresistance or giant magnetoresistance sensors to read back the ones and zeros that are recorded on hard disk, right? Uh, so this is quite popular even now. Uh, the Even though the record head is inductive, but the playback head is resistive, right? Magneto resistive type of sensor. Okay. Uh, so we saw different types of inductive sensors, and in that the LVDT and the variable reluctance are what we call it as passive sensors, because you need an excitation to On the other hand, the proximity sensor or electrodynamic sensors are active inductive sensors. Right? Uh, we also use inductive sensors in other applications. When we come across those applications, I will talk about them. For example, seismic transducers, which are used to measure earthquakes. Uh, the electrodynamic principle and the inductive sensing is employed there, but that's slightly little more complicated. I'm not going to bring it now. We will learn seismic type transducer little later, right? Uh, with this, the inductive type of transducers is over. Then we look at the capacitive type of transducers. Okay. Now, if I look at a capacitance, right? It's easy if I have parallel plates. If it's not a big problem. We can still calculate the capacitance. But if I have two metallic plates with a displacement D and with a dielectric which has a dielectric constant epsilon R, area of the plate is A. Then I have the capacitance here C equal to epsilon naught epsilon R A by, right? So epsilon naught is a constant. We can use capacitive sensor by changing epsilon r, which is done, by changing A, which is also used, and changing D, which is also done. If you have looked at the inductive, we did not touch A, even though mu r is still used. It's not uh, a big application, but we never touch the area A. But in capacitive type of transducers, sensors, we do use the area A. Now we look at epsilon r. The epsilon r, the relative permittivity, right? I'm sorry, its relative permittivity of a material can be used. Applications are very specific to the use, right? So, for example, paper industry, right? So, what we do is we make paper and send it on a conveyor belt so that the paper dries and then rolled out, right? This is paper at the end. So it starts with a pulp, right? Uh, so it's a very long, sometimes even a kilometer long process belt. By the time it comes to the end, you want the paper to be completely dry, no moisture in it, so that the paper doesn't uh, degrade very quickly, because if you have wet paper, immediately organisms will start growing, and in no time your paper will not at all be there sometimes, right? uh, so what they do is they put a hot air here and dry the paper. Now the paper is moving, the air is also moving, so you need to adjust the velocity of the paper and the temperature, because I can't put a large temperature, the paper will burn. So I'll have to ensure that the temperature is not as high to burn the paper. At the same time, I move the paper with a particular velocity. I remove all the moisture inside the paper. So how do we sense whether there is a moisture inside the paper? What we do is we put two parallel plates, right? and send the paper in between, right? If the paper is wet, of course it will be conductive, first of all. Second is the dielectric constant of the paper will have a very large complex component, right? So if I look at the dielectric constant of the paper versus the capacitance, this is actually capacitance. I call this as terminal AB. So capacitance AB, you will get, you won't get a very linear characteristic, you will get something like this, right? But it's not a big problem, we can linearize it. I'll talk about linearizing nonlinear characteristics of capacitors a little later. So, because epsilon r is proportional to moisture, we can say this is also moisture, right? So what you do is you take the capacitance value, right? You ground this, take the capacitor value, compare it with a reference value, right? Reference value of the capacitance is that the capacitance that you would get if the paper is completely free of moisture, right? And then control the airflow or control the speed. So this is normally a multivariable control, speed and the temperature of the hot air, both are adjusted so that you get a moisture free paper which you can roll and sell without bothering whether the paper would deteriorate or not. The paper would not deteriorate. Okay. This another application, instead of paper, you have textile, right? When a new fabric is made, they do what is known as Sanforizing. Again, you can Google search Sanforizing. Whenever you buy a new cloth, you see that the cloth is very shiny on the outside, on the top, and after 2-3 washes you will see that is gone, right? So you can always identify whether a cloth is new or it is washed, right? That is mainly because the cloth manufacturers before they pack the material do this particular process, Sanforizing. So what they do is they slightly wet the cloth and then expose it to high temperature flame, right? The cloth is drawn here with a velocity v, right? Once again we use a capacitive sensor and sense whether oh, it's not here, sorry, flame will not be here, flame will be before the capacitive sensor. So once again use the capacitive sensor value, because the moment I sanforize, the dielectric constant of the fabric would change drastically, and that is what will be reflected by the value of the capacitance, right? And you once again check whether that value is achieved. Till then you keep sanforizing, right? You keep I would call it as polishing the new cloth, right? That's another uh, application for epsilon r changing the capacitance value, right? Uh, Another, again in the textile industry, this is one in spinning, right? So what you do is you have cotton or whatever it is, it could be even synthetic fiber, right? And you have to make the thread and then weave the thread to get a cloth. right? So how do you make a thread? Normally cotton is combed, cleaned, and then made into uh, a long kind of rope, which is again reduced in diameter, reduced in diameter, reduced in diameter, and twisted. Right. Finally, I get a very thin fiber uh, or thread, as we call, and that you wind on a bobbin and use it in the machine to uh, weave the whatever cloth you want. Okay, this again, uh, when you have the preform cotton like this is normally about a few centimeters, right? If you really look at it, it doesn't look like a rope or something like that. It's like a very fragile system, but still will be like a cylinder. So if and only if this preform is uniform, right? I put wherever I check, I should get the same diameter, right? Then only I will get my thread also uniformly thin. Otherwise, the thread will be something like this, right? So somewhere it will be bulging and somewhere this is not at all preferred. The value is very low if you don't have a good quality thread. So to ensure that the preform before it gets into converted into a thread uh, uh, is made such that you have uniform diameter across, right? So this equipment is called auto leveler. So what you do is you make several free forms, right? Let's say 1, 2, 3, 4, 5, 5 free forms, and then put all of them together. Right? 1, 2, 3, 4, 5 in a longish tube and squeeze it to draw one particular diameter, right? The idea is their auto levelers have either 4, 8, 16 as inputs and then only one output, right? Uh, the speed which you draw is also controlled by putting a capacitive sensor here. So what you do is you put a tube around it, and the if the amount of cotton is high, of course your capacitance will be high. If the amount of cotton is low, if your capacitance will be low. So take the value and control the input as well as control the draw speed, right? How fast you are pulling the cotton preform. That is again a capacitive sensor. uh, all this, as I said, uh, specifically use the relative permeability uh, to sense whether there is enough material is there or whether it's a particular material that I am looking at, right? Uh, then you also we saw this epsilon naught, epsilon r, a by d, c. We see epsilon r dependent capacitive sensors. Uh, as I said, they are used in textile industry. They are used in the paper industry, wherever you can look at epsilon r. They are also used in the leather industry, right? When you are tanning the leather or when you are processing the leather, uh, you can once again find out your process parameters by simply measuring the dielectric constant of the leather in terms of the capacitance value that you get on a capacitive sensor. Okay. So that's one other application, right? Now we look at A, as it said, already said, unlike the inductive transducer, where area is not at all used, we use area in capacitive sensor quite extensively, right? So there are several ways of doing it. The first way is that I have a structure like this, right? So I also have structure. Okay, this again. Right? Two, let's say, serrated uh, right? So you fix one of them and move the other, right? So I'm going to take only one teeth, right? So I have, this is the bottom teeth. Again, I am not looking at the depth. This, let me say, is W, and this is capital X. This is also capital X, right? And the movement is small x, right? So if I have the two teeth of the top and bottom plates exactly aligned, right? So this, we already said, this is x, this is x, this is, let's say, a small displacement d, and this is w, right? So if I look at each, this one is x, so the depth is w, x into w will be the area of the capacitance, right? Uh, the capacitance per teeth would be epsilon naught epsilon r a by d. So that would be, this is epsilon per teeth, one teeth, right? Epsilon naught epsilon r, a we already know, w is the width of the comb like structure, uh, in the x divided by d, right? Now if I move the, right, so I am moving by x. Now what is going to happen? This would be epsilon naught epsilon r w into x minus uh, x by d. I can this, sorry, okay, I can take this as, this is for 1. So for n, I will have n teeth, I will have n, like n, epsilon naught epsilon r w x by d into 1 minus small x by x, right? So this I can put it as c naught into 1 minus x by x. So this value is c naught, again I am multiplying n teeth, right? So I see that the capacitance is varying, right? So sometimes what we do is we put the centerpiece like this, and we put one piece here with the, and we put another piece here which is displaced by capital X, right? Something like this. So if I move this in and out, this capacitor will decrease. So I can write this as C naught into 1 minus X by capital X. This capacitance, right, between this and this, I call this as C1. Between this and this is C2. C1 would be C naught into 1 plus X by X, right? So I can make a push-pull type of capacitive sensor, and but the problem is the whole variation. If I look at this, if this is my displacement, when 0 to X, it will increase or decrease, and then it will go like this every X, right? Because it's a long, okay, so it will keep doing this. But simply counting the number of teeth that has moved, we can extend the displacement to greater than X, right? Uh, Many handheld small displacement sensors use this. Please remember, I have put lot of assumptions. For example, if I have a teeth like this, of course I get the maximum capacitance. I put this as X, this as W, and this as D, right? And I said capacitance is epsilon naught epsilon r A by X into W by D. But there would be a capacitance here also, right? I call it as capital D. Then I would still have another capacitance. Please remember they are in parallel, so the capacitance will simply add up, plus epsilon r X W by capital D, right? Uh, when X here, so this would be C1 or C2, doesn't matter. C1 epsilon naught epsilon r X minus X into W by D. When X reduces here, X increases here, so I will get epsilon naught epsilon r X plus X into W by capital D. So we can factor this into account, but most of the time what we do is we make D to be much greater than capital D. For example, capital D may be centimeters, and the small d will be micrometers, right? We take 100 micrometer air gap and make half a centimeter. Capital D is 5 millimeter, and small d is 100 micrometer, right? So this can be neglected, and you will get a very linear transducer. And if I get push-pull type of transducer. So if I look at the symbol, I have two capacitors, uh, right? So one capacitor is increasing, so this is C naught into 1 plus X by X. This would be C naught into 1 minus X by X, right? The another type of capacitive transducer is called electret microphone. So in fact they are quite popular in the yesteryears, right? They are also called condenser type microphone. Condenser is another old name for capacitor. Okay, so the construction is the same. You have a dielectric, and you have a small air gap, and you have the diaphragm, right? And when you speak, when you have sound waves, this diaphragm vibrates, so the capacitance, so if I look at it between terminal A and B, this is the identical to a capacitance vary, right? So you again have C that varies with respect to the speech that you make. So you can put it in a signal conditioning circuit, and right, I will talk about it's already 46 minutes, so I'll talk about the signal conditioning circuits in the next lecture. Uh, so this is a very popular microphone. In fact, today, if you buy what is known as a sound pressure level meter, right? For example, you have to say what is the volume of sound, whether it is 20 dB sound or 40 dB sound or 120 dB sound. You have a standard SPL meter. The standard SPL meter uses a capacitive microphone because uh, that gives very good response. You can design such that you, when you calibrate, you get so most sound level meters that you can buy today invariably use a capacitive microphone, right? The uh, there are other ways of using the capacitance variation, which we will see in the next class. So I stop here.